Welcome back to Introduction to Machine Learning. I'm Ludwig Brutmann, and in this video I will speak a little bit about computational aspects of finding split points in classification and regression trees. So at the end you should know that monotone feature transformations do not affect the tree in a substantial way. You should understand how categorical features can be treated effectively while growing a card, and you should understand how missing values can be treated in a card by surrogate splits. Let's tackle the monotone feature transformations question first. Monotone transformations of one or several features will neither change the value of the splitting criterion nor the structure of the tree, only the numerical value of the split point. Let's have a look at an example. On the left hand side we have some data points, x and y, so we have one feature, and y is numerical, so we are in a regression setting. And we have a tree corresponding to this data, so just a stump, just a one binary split, and we split with respect to x equals 8.5, and on both sides we have some data points. On the left hand side 3 data points, on the right hand side 2 data points. Now let's have a look at the right hand side here. We have also data points, but now we took the logarithm of x, of the feature. Okay, so log of 1 is 0, log of 7 is 1.9. Okay, the y values, the target is the same, and now we let grow a small tree on those data points, and of course the splitting point here of that feature will be different. So x log splits at 2.1, whereas x splits at 8.5. But if you look at the child nodes, so at the leaves of this tree, you will see that you have the same observations there. You have 3 observations on the left hand side, as in the first tree, and 2 observations on the right hand side, and also the constant predictions in the nodes is equal, 0.83 and 10, because we did not change y. Okay, so monotone transformations of the features do not really affect the tree. It's just the numerical value of the split point that changes. Important, this only holds for feature transformations. Okay, monotone transformations of the target variable can have significant and relevant impact on the tree structure. Let's think a little bit about categorical features. We have here an example of a 3-class classification. So the target is either overcast, rainy, or sunny. We have 3 classes, classification. And we have one categorical feature xj, which has classes a, b, c, d, and e. Okay, and let's say we have just this one categorical feature and no other features. In the root node we have 100% of the data, and split on a categorical feature now partitions the feature levels in 2 sets. Here it's ABC for the left node and DE for the right node. And then if we go on, we split regarding A, B and C, and then A and B is split into A and B. So in the end we have 5 leaves, so 5 terminal nodes, where each feature category has just 1 leaf. Okay, that's is, I hope, somehow okayish. So, but we have some computational problems coming up here. So for a feature with m levels, there are about 2 to the power of m different possible partitions of those m values into 2 groups. The exact number is a little bit different, but well, the basic problem is that the number of splits grows exponentially with the number of categories of the feature. But for regression with L2 loss and for binary classification, we can do some clever shortcuts to not have to try out all the 2 to the power of m minus 1 possible split points. And the basic idea is as follows. So let's say we have a classification task with 0, 1 response, so 0, y can be either 0 or 1, okay, binary classification. Now, what we first do is we calculate the proportion of 1s for each category of the feature on that node. Okay, so on the y-axis we have the relative frequency, on the x-axis we have the category of the feature. So these are 4 categories of this feature. Of course, the relative frequencies should sum up to 1. And then if we go to the next slide, what we did here is we sorted the categories according to these proportions. Okay, so an ascending ordering. So the smallest category is D. This comes at first place. Then the second smallest is A. Then comes B. And then comes C. Okay? We just reordered the categories here. Not that much happened. But now that we have reordered the categories, we can treat the feature as if it was ordinal. So as if there was an ordinal structure in that feature. Which means that we have at most to investigate m-1 splits. Okay? If m is 4, as in that case, we just have 3 splits between D and A, between A and B, and between B and C. So that's way less than 2 to the power of m-1 minus 1. So perhaps you can calculate how many we spare here. And this procedure still finds the optimal split, which is somehow interesting. And the proof is not that trivial. So we have linked you a little bit of literature here. If you want to look this up for 0-1 responses, look at Bryman or Ripley. And for continuous responses, look at Fisher. And there are also heuristics for the multi-class case, so that's a rather new publication here. And what I want to show you now is that this result also holds for regression trees if we use the L2 loss. Okay, how does this work? Basically, it's exactly the same idea, so the plots are also basically the same because we just changed the y-axis here. So now y is some continuous response, maybe from R, and well, on the y-axis now we do not have the probability or the relative frequency of the 2 classes, but the mean of the outcome, but the bars are the same. And we do the same thing. We reorder those categories so that they are in ascending order regarding the mean outcome. And then again, we have 3 split points which we have to investigate and just choose whichever is best from these 3 split points. Okay, let's move away from the categorical features and go at a more or less totally different topic here, so hard cut here. Now we're speaking about missing values. So missing values are basically always a little bit nasty, okay? We like our data to be fully filled without any NAs, without any missing values, but well, in practice there are missing values, so we have to come up with some methods that can deal with missing values as well. So problem is when splits are evaluated, only observations for which the used feature is not missing are used, because we can't really use the others. And this can actually bias splits towards using features with lots of missing values, because we then just look at very few observations, and perhaps these few observations are super easy to separate. And well, then at prediction time, perhaps we have all those missing values again. And this doesn't help us really much in practice. So what do? We use surrogate splits. These surrogate splits can deal with missing values during prediction. How does this work? The surrogate splits are created during training, and these surrogate splits define replacement splitting rules that use a different feature but result in almost the same child nodes as the original split. I have an example on the next slide. When observations are now passed down the tree and the feature value used and the split is missing, then we just use the surrogate split instead to decide to which child the data should be assigned. So let's have a look at an example. Each surrogate split itself is a decision stump that tries to learn the actual splitting rule. Okay, now think about this. We are not trying to learn how to predict the outcome, but we're trying how to predict the splitting rule. So it's kind of a meta question here. Okay, so let's look at this tree with a primary split with respect to sepal length equals 5.8, where we perform a binary classification. So to make it easy, we don't have the third class here of the iris dataset, but just the Zetosa and Virginica. Now, if you want to train a surrogate split, then the surrogate split should optimize a splitting criterion with respect to the question if this is true. So perhaps let's make parentheses here. So we're asking ourselves, and this then is the new target variable, let's say, okay? So we have an example here on the next slide. We add a new column to this data set, which tells us if the sepal length is smaller than 5.8 or not. So 5.1 is smaller than 5.8, so that's true, but 6.4 is larger than 5.8, so this is false. So what we create here is a new target column. Okay, this column is the new target which we try to predict with a classification tree stump. So what we do now is we fit a tree of depth 1, so a stump, using all the features, but of course not sepal length, because then this wouldn't really help us in practice. If it's missing, it's still missing. And well, with sepal length, we could of course always perfectly predict if sepal length is smaller than 5.8. So, well, this doesn't make sense at all. So all the features but sepal length, we use those and fit a tree with those features and try to explain if sepal length is smaller than 5.8 or not. And then this is the surrogate split. What we can do now is, well, train one surrogate split, but of course we could also train several surrogate splits if we also store not only the best one, but a few more surrogate splits. Because what could happen is that other features are missing as well at prediction time, okay? So if the best surrogate split still is missing a lot in the data, it's, well, then we can go to a little bit less well-performing surrogate split, but still then we can do some prediction. So I guess a typical number that I see is trying to learn 5 surrogate splits. But keep in mind that this is, well, kind of a lot that we have to train now, because now for each tree, or for each split in the tree, now we train, in that case, 5 new trees, decision stumps, to explain the split. So, well, this kind of blows up computation and a little bit the memory, but, well, usually classification trees with computers from today are not really a problem at all. So for sensible sizes of data, these surrogate splits don't hurt us too much.